A typical question from Chapter 6 might ask you to compute the probability that a randomly selected individual's exam score is at least 81%. Given exam scores are normally distributed with a population mean and variance of, say, 73 and 25. In Chapter 7, you might be asked to compute the probability that a mean exam score from a sample of 10 is at least 81%. In Chapter 6, we use a sample of size 1, while in 7, we use a sample size larger than 1. This difference alters the shape of the distribution used to compute the probabilities and standard deviation, but not its mean. Instead of being told the distribution used to compute the probabilities is normal, you'll need to determine this in Chapter 7. In addition, you will have to compute this distribution's variance, which is typically the variance of the population divided by the sample size. In the example that we discussed here, the distribution used to compute the probability that the mean exam score from a sample of 10 is at least 81% is normal, only if exam scores are normally distributed, because the sample size is so small. This example intuitively represents the difference between Chapter 6 and 7. Of course, there is more to the story. Sampling error is the absolute value of the difference between a sample statistic and the population parameter estimates. Examples include sampling error for the sampling mean. This exists because the probability that the sample mean will be exactly equal to population mean is 0, because the sample mean could theoretically take on infinite many values, while the population mean is some known value. Sampling error for the sample standard deviation. This exists because the probability that the sample standard deviation will equal the population standard deviation is equal to 0, because the sample standard deviation could theoretically take on infinite many positive values, while the population standard deviation is some given value. Sampling error for the sample proportion. This exists because the probability that the sample proportion will equal the population proportion is equal to 0, because the sample proportion, again, could theoretically take on infinite many values between 0 and 1, while the population proportion is some given value between 0 and 1. St. Andrews College receives 900 applications annually from prospective students. The application form contains a variety of information, including the individual's scholastic aptitude test score and whether or not the individual desires on-campus housing. The Director of Admissions would like to know the following information: the average SAT score for the 900 applicants and the proportion who wants to live on campus. We will now look at two alternatives for obtaining the desired information. Conducting a census of all applicants over the last 10 years, say 9,000, allows us to compute population parameters. Selecting a sample of 30 from the 900 current applicants allows us to compute the sample statistics. If the relevant data for the entire 9,000 applicants were in the college's database, the population parameters of interest could be calculated using the formulas presented in Chapter 3. In the following spreadsheet, we have all information on 9,000 applicants to St. Andrews College over the last 10 years. However, only applicants 1 to 7 and 8,999 to 9,000 are actually shown. The population size, n, is equal to 9,000. The sum of SAT scores of St. Andrews College's 9,000 applicants is 8,940,700. The number of St. Andrews College's 9,000 applicants who want on-campus housing is 6,480. The population mean SAT score equals the sum of the SAT scores divided by the size of the population. Since the size of the population is 9,000, and the sum of 9,000 SAT scores is 8,940,700, the population mean is 993. The population proportion of those wanting on-campus housing equals the number who wants on-campus housing divided by the size of the population. Again, the size of the population is 9,000, and the number of those who want on-campus housing is 6,480. The population proportion is 0.72. To compute the population standard deviation, we need to return to our spreadsheet. Since the population mean is 993, notice I have it written as mu equal 993. The first squared deviation from the population mean is found by squaring the difference between 104, or 1004, and 993, which is equal to 121. The second squared deviation from the mean is found by squaring the difference between 942 and the average 993, which is equal to 2,601. The third squared deviation from the population mean is found by squaring the difference between 890 and the mean 993, which is equal to 10,609. The fourth squared deviation from the population mean is found by squaring the difference between 1,032 and 993, which is equal to 1,521. The fifth squared deviation from the population mean is found by squaring the difference between a score of 857 and the population mean of 993, which is equal to 18,496. The sixth squared deviation from the mean is found by squaring the difference between a score of 1,015 and the population mean of 993, which is equal to 484. The seventh squared deviation from the mean is found by squaring the difference between a score of 1,063 and the population mean of 993, which is equal to 4,900. We continue doing this all the way down to 8,999. The 8,999th square deviation from the population mean is found by squaring the difference between a score of 1090 and a population mean 993, which is 9,409. And then finally, the 9,000th square deviation from the mean is the difference between a score of 1,094 and 993, which is 10,201. The sum of the 9,000 square deviations from the population mean equals 57,642,979. The population standard deviation is equal to the positive square root of the population variance, which is the sum of square deviations from the population mean divided by the population size. The sum of the 9,000 square deviations of the population mean is 57,642,979. Thus, the population standard deviation is 80. Now suppose that the necessary data on the current year's applicants were not yet entered in the college's database. That is, the 900 applications to the college for the current year are stored in some box. Furthermore, the Director of Admissions must obtain estimates of the population parameters of interest for a meeting taking place in a few hours. She decides a sample of 30 applicants will be used. The number of random samples without replacement of size 30 that can be drawn from a population of size 900 is equal to 900 choose 30, which equals 900 factorial divided by the product 30 factorial and 870 factorial, or 98 million times 1 trillion raised to the fourth power. That's a big number. Excel can be used to take a sample of 30 applicants. In step 1, a random number is assigned to each of the 900 current applicants. Excel's random function generates random numbers between 0 and 1. In step 2, the 30 applicants with the 30 smallest random numbers are selected. Because there are 900 applicants at St. Andrews College for the current year, we generate 900 numbers from 1 to 900. In the Excel spreadsheet below, we have typed applicant number in cell A1. In cells A2 to A901, we have generated numbers 1 to 900. In cell B1, we have typed random. Below this, in cells B2 to B9001, we have typed equal rand parenthesis, close parenthesis, and then hit enter, which generates 900 random numbers between 0 and 1. The rows are sorted by first highlighting applicant numbers 1 to 900 in column A and the random numbers that were generated in column B, and then sorting on column B in ascending order. The result of the sorting is shown in this table. In the previous table on the previous slide, all 900 applicant numbers were displayed. In the table below, we have 30 applicant numbers that are associated with the smallest random numbers. After the random sample of 30 applicant numbers have been generated, the office assistant of the college's director of admissions can open up the files associated with these applicant numbers to fill in the rest of the table. In the following Excel spreadsheet, we have typed SAT score in column C and wants on-campus housing in column D. Since applicant number 675 is associated with the smallest random number, it is listed first. The office assistant pulls the 675th applicant file from a box containing all 900 application files. Inside the file, the office assistant finds out that the 675th applicant got a 985 on the SAT and desires on-campus housing. The office assistant pulls the next file, the 34th applicant file, from the box containing the 900 application files. Inside the 34th file, the office assistant finds out that the 34th applicant got a 1002 on the SAT and desires on-campus housing. The office assistant fills in the next 28 SAT scores and housing request in the same way. The 30 SAT scores in the sample from the 900 current year applications to St. Andrews College is 30,299. The number of applicants in the sample, the 30 applicants desiring on-campus housing, is 20. The SAT mean sample score equals the sum of SAT scores divided by the sample size of 30. The sum of the SAT scores is 30,299. The sample mean is 1,009.97. The sample proportion of those wanting on-campus housing equals the number who want on-campus housing divided by the sample size of 30. The number of those who wants on-campus housing is 20. The sample proportion is 0.667. To compute the sample standard deviation, we return to our spreadsheet. Notice that the second column containing the random numbers has been deleted. This means the SAT scores are now in column B. Housing requests are in column C, and square deviations from the SAT mean are in column D. Because the sample mean is 1009.97, the first square deviation from the sample mean is found by squaring the difference between applicant 675's SAT score, 985, from the sample mean, which is equal to 623.5. The second square deviation from the sample mean is found by squaring the difference between applicant 34's SAT score of 1002 and the sample mean of 1009.97, which is equal to 63.52. The third square deviation from the sample mean is found by squaring the difference between applicant 768's SAT score of 913 and the sample mean of 1009.97, which is equal to 9,403.18. The rest of the square deviations from the sample mean are computed in a similar way. For example, applicant 565 had an SAT score of 998. Subtracting the sample mean 1009.97 from this, and squaring that difference is 143.28. The sum of the 30 square deviations from the sample mean equals 211,746.97. The sample standard deviation is equal to the square root of the sample variance, which is the sum of square deviations from the sample mean divided by the sample size minus 1. Because the size of the sample is 30, we divide by degrees of freedom, 29. The sum of the 30 square deviations from the sample mean is 211,746.97. The sample standard deviation is 85.45. Different random numbers would have identified a different sample, which would have resulted in different point estimates of the population mean, the population proportion, and the population standard deviation. The table below summarizes the difference between population parameters and sample statistics. The population mean is 993. The sample mean is a point estimator of the population mean. Plugging numbers into this procedure yields a point estimate of 1009.97. Because we can theoretically sample the population infinite many times, the resulting sample means will hover near the population mean of 993. Sometimes the sample means will be below 993, and sometimes they'll be above it. The population standard deviation is 80. The sample standard deviation is a point estimator for the population standard deviation. Plugging numbers into this procedure yields a point estimate equal to 85.45. Because we can theoretically sample a population infinite many times, the resulting sample standard deviations will hover near the population standard deviation of 80. Sometimes the sample standard deviation will be below it, and sometimes it'll be above it. The population proportion is 0.72. The sample proportion is a point estimator of the population proportion. Plugging numbers into that procedure yields a point estimate of 0.667. Because we can sample the population infinite many times, the sample proportions will hover near the population proportion of 0.72. Sometimes sample proportions will be below the population proportion. Other times it'll be above it. Because we can theoretically sample the population infinite many times, the resulting sample means will hover near the population mean. Most of the time, the sample mean will be either slightly above or slightly below the population mean. On rare occasions, the sample mean will be way below or way above the population mean. Thus, the sample mean has variance. And since we expect the average of the infinite many sample means to be equal to the population mean, the sample mean has a distribution. This distribution is called the sampling distribution of the mean, which is the probability distribution of all possible values of the sample mean. The expected value of the sample mean is mu, where mu is the population mean. As we mentioned previously, we can theoretically sample the population infinite many times. The resulting sample means will hover near the population mean, and most of the time will be near the population mean. Thus, the sample mean is not constant, meaning it has variance. The standard deviation of the sample mean from an infinite population or a very, very large population is denoted sigma with subscript x bar and is equal to population standard deviation divided by the square root of the sample size. The standard deviation of the sample mean for a finite population is equal to the expression in red font times the population standard deviation divided by the square root of the sample size, where the expression in red is referred to as a finite population correction factor. A finite population is treated as being infinite if n divided by n is less than or equal to 0.05. The standard deviation of the sample mean, sigma x bar, is also referred to as the standard error of the mean. Under repeated sampling, using random samples of size n, the sample means are normally distributed with the mean mu and variance sigma squared divided by n when either the data is heavily skewed, the sample size is at least 50, and the population standard deviation is known, or the data is symmetric, the sample size is at least 30, and the population standard deviation is known, or the data is normally distributed and the population standard deviation is known. Recall the population mean, standard deviation, and sample size from the St. Andrews College example were 993, 80, and 30. Hence, the expected value of the sample mean is 993. The standard deviation of the sample mean is equal to the population standard deviation of 80 divided by the square root of the sample size, 30, which is 14.6. We use the standard deviation of the mean for an infinite population because n divided by n is 0.000333, which is less than or equal to 0.05. What is the probability that a simple random sample of 30 applicants will provide an estimate of the population SAT score that is within 10 points of the actual population mean? In other words, what is the probability that the sample mean will be between 983 and 1003? In step 1, we need to calculate the z-value at the upper endpoint of the interval, 1003. The z-value is equal to the difference between 1003 and the population mean, 993. If this was a problem from Chapter 6, we would divide the deviation of the mean, 1003 minus 993, by the population standard deviation of 80. But since this is a problem from Chapter 7, we divide it by the standard deviation of the mean, or the standard error, of 14.6. So the z-value of the upper endpoint of the interval is 0.68. This means 1003 is 0.68 standard deviations above the population mean of 993. In step 2, we find the area under the normal curve to the right of the upper endpoint with a z-value of 0.68. We can use the standard normal table because the SAT scores are considered to be normally distributed. The probability of being less than or equal to 0.68 is found by going to row 0.6 and column 08. The probability of being less than or equal to 0.68 is 0.7517. Because 103 is 0.68 standard deviations above its mean of 993, the probability that the sample mean is less than or equal to 1003 is 0.7517 as well. The sampling distribution of the mean is normal, centered at its mean of 993, and has a standard deviation of 14.6, which was computed by dividing the population standard deviation by the square root of the sample size, 30. 14.6. Because the probability of being less than or equal to 1003 is 0.7517, the probability of being greater than it is 0.2483. You could have gotten 0.2483 by going to row negative 0.6 and column 08 in the standard normal table. In step 3, we need to calculate the z-value at the lower endpoint of the interval, 983. The z-value is equal to the difference between 983 and the population mean of 993, divided by the standard deviation of the mean, 14.6. So the z-value of the lower endpoint of the interval is a negative 0.68, meaning that 983 is 0.68 standard deviations below the population mean of 993. Well, this makes sense because 1003 was 10 SAT points, or 0.68 standard deviations above the mean, while 983 is 10 SAT points, or 0.68 standard deviations below the mean. In step 4, we find the area under the normal curve to the left of the lower endpoint, whose z-value is negative 0.68. The probability of being less than or equal to negative 0.68 is 0.2483. We know this because the normal distribution is symmetric, and the probability of being greater than or equal to 0.68 was 0.2483. You can verify this by going to row negative 0.6 and column 0.08 in the standard normal table. Because 983 is 0.68 standard deviations below its mean of 993, the probability that the sample mean is less than or equal to 983 is 0.2483 as well. To calculate the area under the normal curve between the lower and upper endpoints of the interval, 983 and 1003, we add the area of the lower tail, which is 0.2483, to the area of the upper tail, which is also 0.2483. The area of the tails, or the probability of not being between 983 and 1003, is 0.4966. Subtracting 0.4966 from 1 yields 0.5034. Thus, the probability that the sample mean SAT score will be between 983 and 1003 is 0.5034. Suppose we select a simple random sample of 100 St. Andrews College applicants instead of the original 30. The expected mean of the sample is equal to the population mean regardless of the sample size. In our example, we expect the sample mean to be equal to 993. Whenever the sample size is increased, the standard error of the mean, sigma x bar, also known as the standard deviation of the sample mean, is decreased. With the increase in the sample size to n equal 100, the standard error of the mean decreases to the population mean of 80 divided by the square root of the sample size 100, which equals 8.0. With a sample size of 30, the sampling distribution of the mean is normal, with an expected value of 993 and a standard deviation of 14.6. If the sample size is increased to 100, the sampling distribution is normal, but skinnier and taller because its standard deviation is now 8. The sampling distribution center does not change because we still expect the sample mean to be equal to 993. When n is equal to 30, the probability that the sample mean was between 983 and 1003 is 0.5034. If we follow the same steps to recompute the probability that the sample mean is between 983 and 1003, with n equal to 100, we get 0.7888. Because sampling distribution with n equal to 100 has smaller standard error, the values of the sample mean have less variability and tend to hover closer to the population mean. When n was equal to 30, the probability the sample mean is between 983 and 1003 is equal to 5034. When n is equal to 100, the probability that the sample mean is between 983 and 1003 is equal to 7.7888. This increase in this probability results from the fact that the standard error is smaller when the sample size is larger. In other words, we have more evidence. We're going to most likely make fewer mistakes. A smaller standard error means the standard deviation of this distribution is smaller, making the distribution taller and skinnier. The sampling distribution of the proportion, P bar, is the probability distribution of all possible values of the sample proportion. The expected value of the sample proportion, P bar, is population proportion P, where P is the population proportion. Recall the St. Andrews College example. Even though the sample proportion wanting on-campus housing was equal to 0.667, we expected it to be equal to the population proportion of 0.72. Most of the time, the sample proportion will be slightly above or slightly below the population proportion. Rarely will the sample proportion be way above or way below the population proportion. The previous slide suggests there is a variation among proportions computed from random samples of the same size from a population. Because the sample proportion P bar is analogous to sample mean X bar, and the proportion P is analogous to the population mean mu, the sample proportion can be computed in the same way as a sample mean. In the table to the right, we have the variable vote for Obama. In this table, we have a sample of 10 voters that say they will either vote for Obama or not. The second column of this table is labeled D. In this column, we set variable D equal to 1 if the person in the sample says they are going to vote for Obama. We set it equal to 0 if the person will not vote for Obama. Using variable D, we can compute the sample proportion by summing the values of D and then dividing this by sample size 10. The sum of the values of variable D is equal to 6, which is the number of people in the sample that say they are voting for Obama. The sample size is 10. Using values of the variable D from the previous slide and interpreting proportion 0.6 as the population mean and using the equation for the population variance, the variance of variable D is the sum of square deviations from mean 0.6 divided by the number of values in variable D, which is 10. Since there are only two possible values of variable D, we use red and blue to identify them. We use red to identify the values of D that equal 1 and use blue to identify the values of D that equal 0. Now, we should have divided by n minus 1 instead of n because the data came from a sample. However, in most cases involving sample proportions, the sample is very, very large. Hence, dividing by n or n minus 1 yields roughly the same number. Now, since there are 6 ones and 4 zeros, we can use algebra to collect like terms and rewrite the variance of D as the sum of 6 times the square deviation from the mean associated with D equal 1 and 4 times the square deviation from the mean associated with D equals 0 divided by 10. This equals 0.6 times 0.4 squared plus 0.4 times 0.6 squared. This 0.6 comes from dividing 6 by 10. This 0.4 comes from subtracting 0.6 from 1. This 0.4 comes from dividing 4 by 10. This 0.6 comes from subtracting 0.6 from 0. And notice that the negative is gone because a negative squared is positive. Factoring 0.6 and 0.4 from the sum yields 0.6 times 0.4 times the sum of 0.4 and 0.6. Since the sum of 0.4 and 0.6 is 1, the variance of D equals 0.6 times 0.4, or 0.24. Because the proportion who voted for Obama equals 0.6, and the proportion who did not vote for Obama is 0.4, the variance of D can be computed much easier by simply multiplying the proportion who voted for him times the proportion who didn't vote for him, 1 minus p. The standard deviation of variable D would thus be the positive square root of the proportion that voted for him times the proportion that didn't vote for him. The standard deviation of sample proportion from an infinite population, denoted sigma subscript p bar, equals the standard deviation of variable D divided by the square root of sample size n. So there's really nothing new here. This is identical to the sampling error of the mean, replacing the numerator with what it equals, square root of p times 1 minus p, and replacing the ratio of two square roots with the square root of a ratio yields the equation that is shown in the textbook. This is referred to as the standard error of the proportion. For a finite population, the standard error of the proportion is the finite correction factor, the red expression, times the square root of p times 1 minus p divided by the square root of n. The sampling distribution of the proportion can be approximated by a normal distribution whenever the sample is large. The sample size is considered large whenever the following conditions are satisfied. The sample size times the population proportion is greater than or equal to 5, and the sample size times the difference between 1 and the population proportion is greater than 0.5. Recall that 72% of prospective students applying to St. Andrews College desire on-campus housing. This is the population proportion. What is the probability that a simple random sample of 30 applicants will provide an estimate of the population proportion of applicants desiring on-campus housing that is within 0.05 of the actual population proportion? For this example, with a sample size equal to 30 and the population proportion equal to 0.72, the normal distribution is acceptable approximation because the sample size times the population proportion is equal to 30 times 0.72, which is equal to 21.6, a number that is greater than or equal to 5. And the sample size times the difference between 1 and the population proportion is equal to 30 times 0.28, which is equal to 8.4, a number that is also greater than 5. The distribution of the sample proportion is the following normal curve, whose center is at 0.72, the population proportion. The standard deviation of the sample proportion is equal to the square root of the product of p and 1 minus p divided by the square root of the sample size, which is equal to the square root of 0.72 and 0.28 divided by the square root of 30, which is 0.082. 0.67 is 0.05 below 0.72, while 0.77 is 0.05 above 0.72. But we want to know the probability of being between 0.67 and 0.77. In step 1, we calculate the z-value of the upper endpoint of the interval. All we do is we take the difference in 0.77 and the mean, the expected value of the proportion, 0.72. Divide that by the standard deviation of p bar, which is also known as the standard error of the proportion. So we get a z of 0.61. This means 0.77 is 0.61 standard deviations above the mean 0.72. Next, we find the area under the curve to the right of the upper endpoint. Z is equal to 0.61. We go to row 0.6, column 01. The probability that Z is less than or equal to 0.61 is equal to 0.7291. Since 0.77 is 0.61 standard deviations above the mean, the probability that p bar is less than or equal to 0.77 is equal to 0.729 as well. The probability that the sample proportion is less than or equal to 0.77 is 0.7291. The probability the sample proportion is greater than or equal to 0.77 is 0.2709. The z-value of 0.67 is equal to the difference between 0.67 and the population proportion divided by the standard deviation of the sample proportion, which equals 0.61, negative 0.61. Now this makes sense because 0.67 is the same distance from the population proportion, 0.72, as 0.77 is. One is above the population proportion, while the other is below it. In step 4, we find the area under the curve to the left of the lower endpoint, 0.67. Because the probability that z is greater than 0.61 is 0.709, by symmetry, the probability that z is less than negative 0.61 is 0.2709. Because 0.67 is 0.61 standard deviations below the population proportion, the probability the sample proportion is less than 0.67 is equal to 0.2709. Because the probability that the sample proportion is less than 0.67 is equal to 0.2709, and the probability that the sample proportion is greater than 0.77 is 0.2709, The probability the sample proportion is not between 0.67 and 0.77 is equal to 0.5418. The difference between 1 and 0.5418 equals 0.4582. Thus, the probability that the sample proportion of applicants wanting on-campus housing within 0.05 of the actual proportion is 0.4582.